Alright, so introduction to inverse trigonometry. So, so far in the amazing world of trigonometry, you have seen inverse functions such as sine minus 1 of x, or cos minus 1 of x, and tan minus 1 of x, and you have kind of just realize that they're there and pressed a few buttons on your calculator without really understanding what you're doing or what it means to take the inverse of a trigonometric function. So this topic dives deeply into inverse trig functions and then later further trigonometric functions. So inverse trigonometric functions. So trigonometric functions can also have inverses, but due to the repeating nature of the curves of sine of x, cos of x, and tan of x's, their inverses are not functions. So we know that for a function to have an inverse across its entire domain, it has to pass not the horizontal line test, but the vertical, not the vertical line test, but the horizontal line test. And it's pretty obvious that a sine curve is not going to pass the horizontal line test, which means that the function sine of x does not have an inverse, at least over its entire domain. So to make inverse trigonometric functions, we must restrict the domain of the original function. Now, before we do this, let's recall how and why we restrict the domain of functions to create inverses. So suppose a graph and its relationship has been drawn. The graph of the inverse relation is obtained by reflecting the original graph along the diagonal y equals x. You should all remember that. The inverse relation is given is a function if and only no horizontal line crosses the original graph more than once. In particular, suppose that the function relation is a function. If the function is 1 to 1, then the relation is also a function. And if the function is many to 1, then the inverse is not a function. So what we can do instead is, if our graph doesn't pass the horizontal line test, and we did this in our second topic further functions, such as y equals x squared, if it doesn't pass the horizontal line test, what we can do is restrict the domain of my function. So I can restrict y equals x squared to x is greater than 0 or greater than equal to 0, and then that would have an inverse. Or we could restrict the domain for x to be less than 0, less than or equal to 0, and that would have an inverse, but not at the same time. So a cute little example of taking inverse functions. So if you've got the graph of y is equal to e to the power of x. Now e is a special number that we'll learn about later, and it's called Euler's number. So e to the power of x, if we reflect that upon the y-axis, upon the line y equals x, we get y is equal to ln of x, which is actually a log function, log of base e, and it's a log, which is the inverse of e to the power of x. And that's true for any exponential graph. So the inverse of 2 to the power of x is log 2 of x, or log x base 2. So restricting the domain, we have seen in inverse functions that all these functions have an inverse over all real values of x. That's a lie. We did restrict the domain. It is possible, however, to create an inverse of any function by restricting its domain to a certain interval. To restrict the domain, we always look at the stationary points of the curve. It's helpful to choose an interval as the domain so that the domain is connected, so we don't want to choose a domain over any asymptotes. It's usually helpful to extend the restricted domain as far as possible, and it may be helpful to choose a domain that includes 0. So an example, explain why the inverse relation of f of x is x minus 1 squared plus 2 is not a function. Well, it's not a function because that graph looks like this. So it's over here, its vertex is 1, 2, and it's not a function because it doesn't cross the horizontal line test. So so doesn't cross horizontal line test. Okay. Define g of x to be the restriction of f of x to the largest connected domain, including x equals 0. Now we can actually do, we can only do this one if we include x is 0. So including x is 0, we're going to restrict it to here. So, but my domain is going to be, g of x is going to be the function, y is equal to, g of x is going to be equal to x minus 1 squared plus 2, but x is going to belong to, or we could just say, x is less than or equal to 1. Write down the equation of the inverse. So we should remember how to create the inverse equation. So we swap x and y. So our original function is y is x minus 1 squared plus 2. Swapping the x and y is x is equal to y minus 1 squared plus 2. So x minus 2 is equal to y minus 1 squared. So therefore, y is going to equal 1 plus or minus the square root of x minus 2. And then we're going to state that x is, or y really, y is less than or equal to 0. We can do that later. The reason y is going to be less than or equal to 1, sorry, I meant to say y is less than or equal to 1, is because the original function restricted the domain to be less than 1. So that means if we restrict x to be less than 1, then y is going to be less than 1 on our inverse. Now on my original function, we also should note that y was never less than 2. So y is greater than or equal to 2. So in this function, x is going to be greater than or equal to 2. Remember, the domain and range of inverse functions swap. Okay, so we're going to sketch these two functions on an axis. I apologize I didn't leave any room. You just do this on the blank page on the other side of this. Don't know why I didn't leave any room. So, sketch both of them. So our original function was y is equal to x squared, but we x minus 1 squared plus 2, but we restricted it to be less than or equal to 1. So this was 1 and this was 2 here. Now if we draw the line y is equal to x on this function, I might draw that graph a bit better to scale. So we're going to say this is 1, 2, 3, 1, 2, 3. So we've got 1, 2. Is that what we said? 1, 2. So it's going to look like this. And then if we draw in the line y is equal to x, my inverse is going to look something like this. It's going to go through 3, like that. Okay, so we did that in our the second topic, further functions, so you should be okay with that. The reason we're doing this is because we need a refresher on how we take the inverse of functions, because we're going to take the inverse of trig functions now. So we can apply this same logic to trig functions. So let's consider the graph of y is equal to sine of x. Now, a very special type of inverse function can be created from y's sine of x due to the periodicity of the graph. We know this graph repeats itself after every 2 pi radians. However, it does not have an inverse function over the domain from 0 to 2 pi. So from 0 to 2 pi, which is one period, or one loop-de-loop as I say it, it doesn't have an inverse because it does not pass the horizontal line test here. So what we're going to do is we're going to restrict the domain using our rules. So the rules suggested that we start at turning point. So here we've got a turning point, here we've got a turning point. And it also said we must include 0 if we can. So we're going to restrict the domain of y as sine of x from minus pi on 2 to pi on 2. So if the inverse function is simply a reflection on y is equal to x, then we get this is equal to the graph of y is equal to sine minus 1 of x. So on the next page I've got that in better detail. So here, or hence, the graph of y is equal to sine inverse of x, or arc sine of x. Arc sine of x you will see, and if you do coding a cos of x, I believe that the function defined in many Python codes, and for example Java, is a cos of x, and that's defined to be sine. I don't know why I wrote cos, sorry. A sine of x. So the function sine inverse of x is defined by a computer as a sine of x. So some special things about sine inverse of x. Number one is that the domain is minus 1 to 1, and the range, no, sorry, the domain is, I've even got that the wrong way around. It's my fault. The domain is minus 1 to 1, and the range is minus pi on 2 to pi on 2. So here's that function there, it looks like that. So a few different properties of sine inverse of x. Sine inverse of x is not an inverse relation of y equals x. It's the inverse relation of the restriction of sine of x to minus pi on 2 to pi on 2. Sine inverse of x has a domain of minus 1 to 1 and a range of minus pi on 2 to pi on 2. It's an increasing function, and it also is tangent to y is equal to x at the origin, and is vertical at its endpoint. So this graph, importantly, does not keep going forever and ever. So we don't put arrows on the end of this graph. It stops at the restriction of its domain. Okay. Following a similar logic, we can construct the inverse of cos inverse of x. So for cos inverse of x, it's not really appropriate to restrict the domain from minus pi on 2 to pi on 2 because it doesn't pass the horizontal line test. So what we're actually going to do is restrict the domain from 0 to pi, which is here. Now, if an inverse is a reflection upon the x-axis, we yield that the graph of cos inverse of x is this. So its domain is from minus 1 to 1, the same as sine inverse of x, and its range is 0 to pi. So, probably obvious, but cos inverse is not an inverse relation of y as cos of x. It is the inverse function of the restriction of the domain from 0 to pi. Y's cos of inverse of x has a domain of minus 1 to 1 and a range of 0 to pi. It's a decreasing function, and we also could see that cos inverse has a gradient of minus 1 and its y-intercept has gradient minus 1 at its y-intercept and is vertical at its endpoints. Don't worry about that. That's just telling you that it's tangent to a specific function there. We'll do that later when we do calculus. Alright, so tan inverse of x. So here, the graph of tan inverse is interesting because there's lots of asymptotes. So we've said that we don't like to take inverses of asymptotes. We can't, oh, I think we can actually, but we don't like to take the inverse because generally our inverse functions, we want to have it over a continuous point of the domain. So we're going to restrict the domain to be this, from minus pi on 2 to pi on 2. So, no, yes, this does pass the horizontal line test, but it doesn't pass the horizontal line test over its entire domain. So you might think, why don't I make it this and this? Well, no, we don't like asymptotes, so we're going to restrict it for here. Now, when we take its inverse, we actually get this. Tan again is the odd one out. So our domain is going to be from minus infinity to infinity. And that's because the range of tan inverse of x goes up and up forever and ever and ever, amen. So the domain of tan inverse of x, or arctan of x, or a tan of x, is infinity, negative infinity to infinity, and its range is the domain of the original function, pi on 2 to minus pi on 2, or minus pi on 2 to pi on 2. So we get this function. Okay. Some examples of stuff really not involving the graphs, but more just involving inverse relationships. So we're going to use radians for this. Now, when I calculate radians, I still hold on to degrees sometimes. So when I actually use my calculator to find cos inverse of a half, I get 60 degrees. Oops, what happened there? I get 60... Where did all my writing go? I don't know. I get 60 degrees. So I might write 60 degrees here, and then I'm just going to manually make that 60 on 180, which is pi on 3. Now we also should know that, and something I have not paid attention to, is that there's a minus here. So yes, cos inverse is 60 degrees. Cos inverse of a half is 60 degrees. But using all stations to central, cos is only negative here and here. So cos inverse of x is going to be 180 minus 60, which is 120, and 180 plus 60, which is 240. Converting that to radians, we get 120 divided by 180 is 2 pi on 3, and 240 divided by 180 is 4 pi on 3. So tan inverse of minus 1, well, you just need on your calculator, don't ever type in tan inverse of minus 1, type tan inverse of 1. That's same with this one here. Never ever type into your calculator cos inverse of minus a half. Type in cos inverse of a half and then use all stations to central. So tan inverse of a half is 45, of 1 is 45 degrees, but it's negative 1, so all stations to central. Tan is negative here and here, so it's going to be equal to 180 minus 45, which is 135, and 360 minus 45, which is 315. Converting that to radians, 135 divided by 180 is 3 pi on 4, and 315 divided by 180 is 7 pi on 4. Okay, to find tan inverse of tan of 5 pi on 6, well, we're going to realise that tan of 5 pi on 6 is equal to minus 10 of pi on 6, because 5 pi on 6 and pi on 6 are equivalent, and in terms of our angles, and tan is negative in the second quadrant. Now tan of pi on 6, if you type it into your calculator, is 1 on root 3. So my answer is minus 1 over root 3. Now I like to explain what we have to do here with a graph. So we're trying to find tan inverse of tan inverse of 1 over root 2. Actually minus 1 over root 2. Now the important thing to note is that my tan inverse graph can only exist from pi on 2 to pi on 2. In other words, my graph can only exist in the first and fourth quadrants, which is where tan is, so then that's because that's between pi on 2 and minus pi on 2. So minus pi on 2 and pi on 2 exist here, because up here is pi on 2, down here is minus pi on 2. But let's think about what it means to take tan inverse of 1 on root 2. We know one of them has to be negative. So we could say, okay, if I draw my triangle, and we've got theta here, and this is going to be 1, and this is going to be root 2, and that's going to be minus 1 because we're going down by 1. So if we were to take tan inverse of that, we're going to think about what we would get. Well, tan inverse of 1 on root 2 is 30 degrees, which is pi over 6. But we can see that this lies in the 4th quadrant. So our theta has to lie here. Our theta is here. Now, if we go backwards, our theta is minus pi on 6. But if we go this way, my theta is equal to 2 pi minus pi on 6. So 2 minus 1 on 6. Which is 11 pi on 6. So my answer is going to be pi on 6 or 11 pi on 6. Really, they do mean the same thing though. So minus pi on 6 or 11 pi on 6. Okay. This next one here, cos inverse of cos of 5 pi on 4. Well, cos of 5 pi on 4 is the same thing as saying cos of pi on 4. But 5 pi on 4 exists in the 3rd quadrant, and cos is a negative in the 3rd quadrant, so it's minus cos of pi on 4. Now, cos of pi on 4 is equal to 1 over root 2, so minus 1 over root 2. So we're trying to find cos inverse of minus 1 over root 2. But remember, my cos inverse graph has a domain that's restricted to from 0 to pi. In other words, the graph of cos inverse, it can only exist in the 1st and 2nd quadrants, because this is 0 and this is pi. So it has to be negative somewhere. So to calculate cos inverse of 1 on root 2, that's going to be theta. This is going to be minus 1, because remember, this is just like an xy plane. This is the vector, minus 1, and then we're going up by root 2. Now, cos inverse of 1 on root 2 is equal to pi over 4. But that makes this value here pi on 4. But the actual value of cos inverse of minus 1 on root 2 is not pi on 4, but pi minus pi on 4. Because we're trying to find this one here. We're trying to find this angle here. So pi minus pi on 4 is 3 pi on 4. Okay. Those questions are a lot harder than what they look like. Okay, in each part, use a right-angled triangle to find the exact value of. So, sine of cos inverse of 3 on 5. So we go, okay, if we make this theta, then cos inverse of 3 on 5, well, this has to be 3, this has to be 5. Using Pythagoras' theorem, that's 4. So sine of this is just going to be, so sine of cos inverse of 3 on 5 is just going to be opposite over hypotenuse, 4 on 5. In a similar way, we're going to say this is theta. This would be 5, that would be 13. Using Pythagoras' theorem, this is going to be 12. So tan of sine inverse of 5 on 3, 5 on 13, sorry, is equal to opposite over adjacent, which is 5 over 12. Okay, and last thing, question number 8. We've got, let theta be equal to sine inverse of minus x. So part A is use the fact that sine minus theta is equal to minus sine of theta to show that theta is minus sine inverse of x. So if we let theta to be equal to sine inverse of minus x, well, that would imply flipping it back the other way, that would imply that sine of theta equals minus x, which would make x equal to minus sine of theta. Now, we know that sine of minus theta is equal to minus sine of theta. So, using that information, x is going to be sine of minus theta. Swapping that all around, that would make theta equal to minus theta equal to sine inverse of x, or in other words, theta is minus sine inverse of x. Okay. Part B, well, we've said theta is equal to sine inverse of minus x, but we've just proven here that also theta equals minus sine inverse of x. So therefore, sine inverse of minus x equals minus sine inverse of x. Done. Okay, hope that helps.